Now let's go through several coherence protocols one by one, starting with the MSI protocol. As you can see from the table in the lower right-hand corner of the slide, the MSI protocol is a three-state invalidation protocol. In later videos, we will consider a four-state invalidation protocol, MESI, a three-state update protocol, Firefly, and a four-state update protocol, Dragon. With each of these protocols, we will start with the state diagram and then proceed with an animation showing how the protocol operates. The three states of the protocol are first, the invalid state. This should be familiar from the write-through protocol. It just indicates that the block is not cached or was cached but has since been invalidated. The second state is the shared state. In this protocol, if a block has not been written into by any processor since being loaded, copies of this block can exist in multiple caches. Since it hasn't been written into, we say that it is clean or up to date. The third state is the modified state. This is a block that has been modified since it was fetched from memory. Sometimes we call a modified block dirty. A block that has been modified can be held in only one cache. It is the job of the protocol to enforce this. As we go through the protocol, we process a set of events, such as reads and writes. If the event is caused by the current processor, that is, the processor whose cache we are observing, it is called a processor event. The two processor events are PRRD for processor read and PRWR for processor write. Transactions that are initiated elsewhere in the system come to our processor over the shared bus. In this protocol, there are three bus transactions. First, bus read, which means that another processor has requested a read-only copy of the block from memory. Processors in memory are on the bus, so this request must go across the bus from processor to memory. Bus read X, which asks for a copy of the block that is going to be written. You might think that that would be a bus write transaction, but it's really more than a bus write. Only one word is being written, but the whole block needs to be fetched into the cache before or during the write. For that reason, it's called a bus read X for bus read exclusive. It's called exclusive because after it occurs, only one cache is allowed to have a copy of this block. The write that is taking place will modify the line. And flush, which means that a cache line is sent across the bus to update memory. This will happen when a block is replaced because of a cache miss to some other block, or when another processor requests a copy of a block that has been modified since it was cached. When a read or a write occurs, the cache state must be updated accordingly. In most cases, a bus transaction will be needed, and sometimes a cache line needs to be flushed onto the bus. These protocol actions are represented in the state diagram and in our animation. We're about to see our first state transition diagram. First, we'll see the diagram for processor-initiated transactions, and then the diagram for bus-initiated transactions. We'll follow that up with a state diagram showing all transactions, both processor-initiated and bus-initiated. When a line in any state moves into state I, that's an invalidation transition. When a line in state M, the exclusive or modified state, moves into the shared state, that's called an intervention. We see the three states of this protocol, M, S, and I. If a processor writes a block that it hasn't already cached, that's a processor write transaction out of state I. It causes a bus read X transaction on the bus because it must write a word to the line, which means that any other cache holding the block must transition the affected line into the invalid state. If a processor reads a block that's not in its cache, that's a processor read transaction out of state I. It causes a bus read transaction because the processor just needs to fetch a clean copy of the block. It doesn't need to cause any other caches to change state. If a processor reads a block that's already in its cache, that's a processor read transaction, but main memory does not need to be referenced, so there's no bus transaction. There's also a way that a line can transition from state S to state M. Think for a moment of what might cause that. That's when a processor writes to a line that's already in its cache. The line transitions to state M, and a bus action is needed because any other cache holding a copy of the line must be invalidated. Note that when I say the other cache is invalidated, what I really mean is that the affected line in the other cache is invalidated. See if you can state in another way why the bus read X is needed. If a block is cached in state M, then the processor that has it cached is allowed to read or write it without any bus activity. We know that it doesn't affect any other processor's cache because no other cache can hold a copy of a block we have in state M. Now let's look at the bus transactions. If our cache has a line in invalid state and another processor reads or writes the block, this will come in as a bus read or bus read X transaction across the bus. Our cache doesn't have to take any action because the line is already invalid. If our cache has a line in state S and something comes in over the bus, it will stay in state S. What are we talking about? We're talking about a bus read. That is to say, if another processor reads a block that we have in shared state, we don't need to do anything about it. We just stay in shared state. The fact that we don't do anything means that the other processor needs to read the line from memory. As we will see later, some protocols implement cache-to-cache transfers where a cache is responsible for sending a copy of its line to another cache. However, the MSI protocol doesn't do that. If our cache has a block in state M and another processor reads the data, we see that as a bus read coming in over the bus. In this case, our cache does need to take action. It changes its state to S, flushes the block to memory, and the other processor can pick up the block as it goes across the bus. Then there are two other transitions from the other states to state I. See if you can tell us what they are. The first is a bus read X that comes in when our cache is in state M. It induces a flush operation because our cache needs to update main memory at the same time that the requesting processor's cache is picking up the block. On the other hand, if we are in state S when a bus read X transaction comes in, we just invalidate the block without flushing it, since main memory is already up to date. Now we can put it all together and display the processor-initiated and bus-initiated transitions on the same diagram. Note that in this diagram, state M is at the top, with state S in the middle and state I at the bottom. This signifies that when a cache has a block in a higher state, it has more control over that block. Now we are ready to watch the animation. It starts with all caches empty and the value of A in memory being 1. In this animation, we will only be interested in one variable, even though a cache line is much larger than needed to hold one integer value. Note that the processors and caches are shown above the bus and memory is shown below. Each cache has a snooper, which examines all bus transactions. At the lower left is our instruction sequence, or trace. It consists of 7 instructions. We will show what happens to memory and caches when these instructions are executed. First, P1 reads A. From the view of P1, this is a processor read. Since P1 does not have A cached, this is a cache miss and results in a bus transaction to fetch the block containing A. Main memory responds to the bus transaction and forwards the block to P1. P1's cache caches the line containing A in shared state. Now the read operation is complete. Next, P1 changes the value of A to 2. From P1's perspective, this is a processor write. Since A is in the cache, the write is directed to the cache. But since the line was in state S, it had to change to state M. Thus, a bus read X transaction is required for P1 to get exclusive access to A. When the bus transaction finishes, the write operation completes. Now P3 reads A. This is a cache miss, so a bus transaction occurs. Before memory responds, P1's snooper notices that another processor is reading, so it needs to downgrade its access and changes to state S. Because P1 has the only up-to-date copy of the block, it flushes it out over the bus where it is picked up by P3 in main memory, and the read operation completes. Next, P3 writes A. Because its copy of A is in state S, it can't write it without issuing a bus read X. The bus read X is snooped by P1, which has to invalidate its copy of A. Meanwhile, P3's write completes, changing the cached value to 3, and the write operation completes. Now, P1 tries to read the value of A from its cache. But since its copy is invalid, it needs to issue a bus read to read it. P3 snoops this bus read and flushes the block out over the bus, where it is picked up by memory in P1's cache. The read operation completes. Now, P3 reads A from its cache. This is a cache hit, so the cache simply returns the data. No bus transaction takes place. The read operation completes. Now P2 finally gets into the act by issuing a read for A. Since it's a cache miss, it requires a bus transaction, namely a bus read. The memory controller observes the bus read. Memory responds and sends the block containing A to P2's cache. The read operation is complete. Now all three caches have valid copies of the block in state S. This table shows which caches have the block in which state after each instruction. It also shows which bus action takes place at each step. We've assumed that when a line changes from state S to state M, a bus read X is issued. But our system might also support a bus upgrade transaction, in which case the line can change from state M without the block having to be sent across the bus to the requesting processor. Also notice where the data comes from. It comes from memory, except in the case of a cache hit, or when the up-to-date copy of the block resides in another cache. One transition we didn't see during our animation was an invalidation of a block in state M, as would occur when two different processors write the same block in sequence. At first glance, you might wonder why a flush is needed. Why can't the second processor just read the line from main memory and then overwrite the write that was performed by the first processor? There are two reasons for that. First, it could be a read with intention to write, something like an increment instruction, where the existing value needs to be read first. Or the second processor might write to the same block, but to a different word in the block. Then, to stay current, it also needs to see the word that was changed by the first processor. As we just saw, if the write was to a shared block, we don't actually need to read the data again. We can use a bus upgrade transaction if our bus provides one. Also, notice that a cache miss causes two blocks to change state. The block that is being replaced, that's the victim, changes to state I, and the block that is being brought into the cache changes to some other state. When a block is flushed, it is flushed to the requesting cache and to main memory. That avoids the need for separate bus transactions to update main memory. Finally, note that a write anywhere in the line will invalidate the same block in all other caches. So even words in the line that have not been written will be purged from all other caches. Looking back at the previous page, suppose that word 0 of the line was read by all read operations, but the write by P3 was to a different variable on the same line, say to B, which was stored in word 1 of that line. The second R1 would still miss, but now it would be a false sharing miss. Is MSI coherent and sequentially consistent? Well, are the conditions of write propagation and write serialization met? Write propagation is met because any write anywhere in the system will cause all other copies to be invalidated, and they will be refetched from memory the next time they are read. Write serialization is read because all writes are serialized over the bus. Sure, there are some writes to cache lines that are already in state M that don't go onto the bus, but in this case no other processor is using those words, and before any other processor uses them, there will be a bus transaction. For sequential consistency, all writes to all locations are serialized on the bus whenever they need to be visible to more than one processor. As soon as a write has gone across the bus, we know it's visible to all processors. Any read will then return the latest value written.